Okay, starting energetics part 2. We're going to start off just with energy. And the definition of energy is the ability to do work. And it's typically equal to force times distance, with the units newtons times meters. Right. Getting back to enthalpy, standard enthalpy is typically in the units of kilojoules per mole. And this is normally measured experimentally, okay, by measuring a temperature change of water or surroundings. All right, a couple things that we need to keep in mind, or I'm just going to name one as we go along, there'll be more. The heat capacity of water is equal to 4.18, and that is joules per gram degrees Celsius. Remember that delta T in degrees Celsius is the same as delta T in Kelvin, because you're talking about the change. All right, so let's look at just a quick example, and we're going to look at a spirit lamp or burner example. I'm going to pause this and draw a diagram and then come back. Okay, so what I've drawn is a spirit burner. This is stirring. All right, so here we have a container. I'm going to use a different color. Okay, so here we have a container, metallic, full of water. There's a thermometer in it to measure temperature. There is some stirring going on. In the bottom of this we have a small container of liquid fuel that can burn, and I did draw a flame using color. All right, so when we run an experiment like this, what we're interested in doing is finding the delta H of combustion for this liquid fuel. Okay. Some of the data that we would be collecting is going to be the mass of the spirit burner. Okay, and typically, and that's initial. That's going to have an uncertainty of 0.001 grams. For example, we're going to find the mass of the spirit or the liquid fuel final, and that's also going to have that uncertainty. We're going to measure the change in temperature, and let's call that uncertainty 0.5 degrees, 0.5 degrees. And then we're going to have the mass of water. And the mass of water is typically going to be more than the spirit, so we use sometimes a different scale for that, plus or minus a gram. If you remember from the energetics, we are going to use the formula Q is equal to mc delta T, where the mass is going to be the mass of the water. The heat capacity is taken to be that of water, grams degrees Celsius, and the change in temperature will be the change in temperature of the water. Remembering that Q of the water is going to be negative Q of the spirit or the fuel. And that the change in enthalpy combustion for that fuel is going to be Q of the spirit over the moles of the spirit. Okay, and spirit meaning that liquid fuel. All right, there are usually large errors associated with this experiment type, and those would be may not have complete combustion. If you think for a minute, how would you prove that? What kind of observations might you see? Observations would have a yellow flame and the production of soot. Then another reason why you may have large error is not all of the heat is transferred to the water. You're going to lose some to the surroundings. You also have to heat. You have to heat the thermometer, the container, and the stir bar. Okay. Also, some of the spirit, because they are typically volatile components, some of it may have evaporated. Okay. Now for this particular experiment, we're just going to look a quick moment at the uncertainty. And reason being is you are more than likely going to get a question that pertains to data or experiment. All right, so just real quick, remember percent uncertainties is going to be the uncertainty, and if we take, for example, the mass of water, it would be plus or minus that 1 gram over, say we had 150 grams, that's what we measured out. All right, or just the mass of the water. I just threw that in as an example, don't ask me where I got it from. All right, times 100%. The percent uncertainty for the mass of the spirit would be equal to plus or minus 0.002 grams. Remember, we have to add both of those uncertainties for the initial and the final over the mass burned times 100%. Okay, and the percent uncertainty of the temperature is going to be the plus or minus 0.5 degrees Celsius over the change in temperature times 100. To get the percent uncertainty for the experiment, you add these. Okay, if this is less than 5%, you had a precise lab. Okay. Let's take a quick look at the reactions in solution. You're going to use the same Q is equal to MC delta T. This M, though, is going to be the total mass of your solution. And you typically assume a density of water which is 1 gram per milliliter. And you're typically adding two solutions together, so you would just add the total volume times that density. Hopefully you remember that you should get a temperature graph, temperature over time, starting here, then we start the reaction, and it should go like that. I'm exaggerating perhaps a little bit, but remember that what you need to do is extend this graph up. Okay, and what you want to do is actually this right here is your final temperature. This accounts for some heat loss of your system. Okay, and that'll be the second screencast for energetics.